Good day, students. Welcome to the first part of the geometry CST review. I'm going to be going over questions 1 to 20 on the release questions on the CDE website. Okay, so if you want to find this document, you can find it on the internet. Just go to Google and then just type in geometry CST released. Enter, and the second link will take you to the document where you have all the release questions, and then just scroll down to geometry, click on that, and that will give you the document that I'm going over today. Okay, you can print it and have the answers for additional practice. All right, so with that in mind, let's go over some of these questions. I'm starting from number 1. It says, which of the following best describes deductive reasoning? So basically the whole idea of deductive reasoning is basically P implies Q. Okay, P implies Q. What on earth does this mean? It means that you have, this is like a statement with two parts. The first part is called the premise, P, or the hypothesis, or is also referred to as the antecedent. Okay, and then the second part, Q, right here, this one is a conclusion. You can draw conclusion or the consequence. Okay, consequence. Alright, so anytime you have a logical argument, we have a premise implying a certain conclusion, then that is known as deductive reasoning. Okay, you can draw a conclusion from a given premise. So for example, if you are in California, then that means that you are in US, you are in United States, right? This is an easy conclusion you can draw from this because you know that California sits completely in the United States. So this is an example of deductive reasoning. All right, so let's take a look at these options right here. Which of these fits this description right here? Using logic to draw conclusions based on accepted statements, accepting the meaning of a term without definition, defining mathematical terms to correspond with physical objects, inferring general truths by examining a number of specific examples. Now, the correct answer to this is A, because in option A, it says you join conclusions based on accepted statements. So if you have a premise and you join a conclusion based on the given premise, that's deductive reasoning. Okay, so you can see the keyword here, drawing conclusions from a given premise, hypothesis, or antecedent. Okay, all right, so there you have it. All right, let's move on to number 2. It says, I have number 2 over here. It says in the diagram below, angle 1 is congruent to angle 4. Which of the following conclusions does not have to be true? If angle 1 is congruent to angle 4, you have a situation where these two lines must be parallel. You have two parallel lines cut by a transversal. Okay? Anytime you have two parallel lines cut by a transversal, when the angles look congruent, guess what? They are congruent in most cases, well, in all cases. And if the angles are do not look congruent, so if angles do not look congruent, guess what? They are supplementary. Okay, what does supplementary mean? They add up to 180 degrees. Okay, so that's the rule here always. So for example, look at 1 and 3. Do they look the same? Yeah, guess what? They are congruent because they're corresponding angles. Okay, 2 and 3, do they look congruent? Yes. Guess what? They are alternate interior angles, and then 4 and 1 are alternate exterior angles. Okay, if you look at 3 and 4, these are vertical angles because they're the same. Vertical angles because they're the same. All right, they look the same. All right, so what conclusion can we draw from here? I mean, which of the following conclusions does not have to be true? So angle 3 and angle 4 are supplementary. Even just by looking at this, do these two look like they add up to 180? If I break it down the center like this, both of them are obtuse angles. Both of them are bigger than 180. I mean, they're both bigger than 90 degrees, so if you add them up, your sum must be bigger than 180, so they cannot be supplementary. Okay, so angles 3 and 4 are supplementary angles. This is false. They would have been supplementary if this line were going up and down like this. If they were straight down like this, and this were angle 3, and this were angle 4, and these were right angles, then they'll be supplementary because 90 plus 90 is 180, and that's the definition of supplementary angle. So this is false. Okay, line L is parallel to line M. Definitely, that's what we said earlier. These two lines are parallel. Angle 1 is congruent to angle 3. Yes, because this angle and this angle are corresponding angles. Angle 2 is congruent to angle 3. Yes, because this angle is an alternate interior angle with that angle right here. This is interior, and this is the exterior, and this is the exterior. Okay? Exterior. Alright, so the answer to this one is A, because they do not necessarily have to be supplementary. Two obtuse angles are not supplementary. Alright? Okay, let's move on to question number 3. Question 3. It says, consider the arguments below. Every multiple of 4, if every multiple of 4 is even, 376 is a multiple of 4. Therefore, 376 is even. And then secondly, a number can be written as a repeating decimal if it is rational. Pi cannot be written as a repeating decimal, therefore it is not rational. It says which, if any of these, use deductive reasoning. So basically, deductive reasoning is basically when you have P implies Q, you have a premise, and you're drawing a conclusion from that. This is one version of deductive reasoning. Another version of deductive reasoning is known as a contrapositive, where you say not Q implies not P. Alright? You say basically concluding that the original statement is not false based on the fact that the conclusion is false. So this is known as known as a contrapositive argument. This is a contrapositive. Okay? These two are forms of deductive reasoning. Alright, so let's look at the first one. It says if 4 is even, that's P. If 4 is even is P. Then 376 is a multiple of 4, is Q. I'm sorry, it said every multiple of 4 is even. 376 is a multiple of 4. Therefore, 376 is even. So this is an example of P implying Q. So basically, multiple of 4 implies even. Okay, that's the condition. So 376 is a multiple of 4, that automatically implies that it's even. That's P implies Q. So statement 1 is definitely deductive reasoning because you're drawing conclusions based on the hypothesis. The hypothesis here is that it is a multiple of 4. Okay? And then if you take a look at the second one, a number can be written as repeating decimal if it is rational. So basically, if rational, that implies it can be written as a repeating decimal, So basically, this is your P implies Q. It says pi cannot be written as a repeating decimal, therefore it is not rational. You notice it's switched around. Pi cannot be written as a repeating decimal. Cannot is the opposite or the negation of this. So you basically have a not Q implying that pi is not rational, not P. So when you switch it around like this, you're doing the contrapositive argument, and this is a valid deductive reasoning argument too. So 2 also is true. Okay, so don't forget P implies Q is deductive reasoning, and then not Q implies not P is also a valid argument for deductive reasoning too. Okay, so 1 and 2 are both deductive reasoning. So your answer to letter 3 is C. Okay? Alright, let's move on to 4. For 4, it says a triangle has at most one obtuse angle. Eduardo is proving the theorem above by contradiction. He began by assuming that that triangle ABC, that in triangle ABC, angle AB are obtuse, which therefore will Eduardo use to reach a conclusion. So basically, argument by contradiction is assuming that that the original statement is true, and then you want to arrive at a contradiction. Okay, I mean, assuming that the original statement is false and arrive at a contradiction. All right. So in this argument, it says a triangle has at most one obtuse angle. If you want to argue this, basically you have to say to prove by contradiction. You have to say, oh wait, assume not. Assume not. Okay? A triangle, you have to assume the opposite of this statement and see if you can arrive at a contradiction. Okay, so a triangle, if it does not have at most one obtuse angle, a triangle has more than one obtuse angle. Okay? What does obtuse mean? Obtuse basically means that obtuse angle is basically an angle that's greater than 90 degrees. Okay, so one of these basically saying you have two angles in a triangle that are greater than 90 degrees. So basically, is that possible? That's a question. Can I have three angles with two of them being greater than 90 degrees? Would that result in a problem? If I can arrive at a contradiction or a problem, then I know that the answer is false. So let's take a look at this. So it says if two angles of a triangle are equal, then the sides opposite the angles are equal. That has nothing to do with what we're talking about. This one says if two supplementary angles are equal, then the angles each measure 90 degrees. Has nothing to do with what we're talking about. We know that supplementary angles add up to 90 degrees, but we don't have a triangle here. And then the C says the largest angle in a triangle is opposite the longest side. That's always true, but it tells us nothing. It's not a contradiction to this. How about the sum of measures of angles in a triangle is 180? Wait a minute. If two of them are bigger than 180, if two angles are bigger than 180, for example, let's say we have a triangle like this. So let me just get a triangle for you. We have a triangle like this, and this angle is 99, and this angle right here is 100. Since these two are obtuse, then the sum must be bigger than 180. So the sum of the measure of the angles of a triangle is 180. The sum of this triangle right here, which satisfies my assumption, is 199. So if this were true, the sum of angles, I'll write it down here. The sum of angles in a triangle must be greater than 180. Than 180, which is a contradiction. Greater than 180, which is basically a contradiction to this original statement that the sum of angles in a triangle is 180. This is a known fact, right? So this contradicts that. So this is a contradiction. So the original statement our assumption is false, and the original statement is true. So assumption is false. If assumption is false, the original statement is true. The original statement is true. Okay? Alright, now let's move on to the next one. Problem 5. Let's see. Alright, problem 5 says use the question below to answer the given problem. Um, so it says given that AB is congruent to BC. Now, anytime you're given congruencies, with a figure, you'll always have to mark them accordingly so you don't get anything confused. So AB is congruent to BC. That means this side right here is congruent to that side. Okay, they're the same length. AC is the midpoint of, B is the midpoint of AC. Midpoint means that these two sides are divided evenly, which makes them congruent. So this side right here is congruent to that side. Okay? Prove that triangle ABD, follow the order, ABD is congruent to CBD. So how do you prove that two triangles are congruent? There are four congruency rules that you have to know. Okay? We have the SSS, which means all three sides are congruent. We have the SAS, two sides and the included angle are congruent. AAS, two adjacent angles on a non-included side. This is equivalent to SAA, same thing, okay? These are the same. So there are four of them. We have 1, 2, 3, and then the fourth one is let me see it. Is oh yeah, ASA. It's angle, side angles, so both angles and the included side of both angles are congruent, including the included side. Okay, so let's see what applies here. Please always follow the order, okay, when you're doing when you're using these congruency postulates. Okay, so let's take a look at this right here. AB is congruent to BC because of the midpoint of AC. So these two sides are congruent. That gives us S. We have one S now, so the answer, it could be this, or this. This one cannot be a possible answer because we don't have it in the order of things. And then AD is congruent to CD, definition of midpoint. AD is congruent to DC, that's another S. Ooh, looking good. So last one is BD is congruent to BD, reflective property of equality, that's another side. So we have three sides. That's automatically a SSS congruency postulate. So the answer for this one is D. Okay? Remember that ASS, which is the same thing as SSA, never works for congruency. Do not memorize this. See, ASS or SSA are both wrong, so don't ever use this, okay? These are the only four that work for establishing congruency. Alright, let's move along to the next question. Problem number 6. Question 6. It says, alright, so number 6, we have this triangle right here. So it says in the figure below, if AB is bigger than BC, the figure below AB is bigger than BC. So it says, if we assume that measure of angle A is equal to measure of angle C, it follows that AB is equal to BC. This contradicts the given statement that AB is greater than BC. What conclusion can be drawn from this contradiction? So what can we say about the contradiction? If you arrive at a contradiction, that means the assumption is false and the original statement is true. Okay? So basically, if AB is bigger than BC, that means that this can be one tick and this is double tick. And basically, if two sides are of different lengths are not congruent, that means the base angles are not congruent also. Okay, that means this angle and this angle are not congruent. Remember, if you have an isosceles triangle, let me see if I can do a sketch of an isosceles triangle. If you have an isosceles triangle, if the two sides are equal, it follows that the base angles are also equal. Alright? If the sides are not congruent, then the base angles are not congruent, just like this case. So in this case, we assumed not. So assuming not basically means that we are assuming that measure of angle A is equal to measure of angle C. This is assuming not. Alright? Assume not. Now, that means this statement is false, and the opposite. What is the opposite of this statement? Measure of angle A is equal to measure of angle C. The opposite basically means that the measure of angle A is not equal to the measure of angle C. Anytime you arrive at a contradiction, that means the opposite of your assumption is true. So basically, we know that this angle is not congruent to this angle because this side is greater than this side, or is not equal. Or we can say AB is not congruent to BC because this side is longer than that side. So what conclusion can be drawn from this contradiction? Measure of angle A equal to measure of angle B? No. Measure of angle A is not equal to measure of angle B. That has nothing to do with this side. No. Measure of angle A is equal to measure of angle C. That's what we said was false. So the opposite of that, which is measure of angle A, is congruent to is equal to measure of angle C. That's your answer right there. Okay. All right. So basically, don't forget, prove by contradiction. You assume not, and then you arrive at a contradiction. And then when you arrive at a contradiction, that basically means the original statement, the opposite of your assumption is true. So the opposite of assumption is true. Okay, so that's basically how it works. All right, let's go ahead and move on to number 7. Number 7, where are you? And number 7, it says use the proof to answer the question. This is also another case where you have parallel lines cut by a transversal. How do I know that? You're told here that angle 2 is congruent to angle 3. These are alternate interior angles, and angle 1, but we have to prove that. So if angle 2 is congruent to angle 3, since they're alternate interior angles, it follows that line L is congruent to line M. And whenever you have two parallel lines cut by a transversal, we know that when angles look congruent, guess what? They are in fact congruent. Okay? And then when angles look like they're not congruent, they are basically supplementary. Alright? That's the rule here. Don't forget that rule. Okay? So we want to prove that angle 1 is congruent to angle 4. So you're given that you told that angle 2 is congruent to angle 3. That's what you're given. Angle 1 is congruent to angle 2. And angle 3 is congruent to angle 4. What on earth is that? Angle 1 is congruent to angle 2. What are these two angles called? Angles that are opposite each other like that are known as vertical angles. Vertical angles. And guess what about vertical angles? Vertical angles are congruent. Same case with 3 and 4. This angle right here and this angle right here, these are vertical angles also, and they are congruent. So which one has vertical angles here? Our answer is B. Okay? Alright, let's move along to question 8. In question 8, we're told that two lines in a plane always intersect in exactly one point. Which of the following describes a counterexample for the assertion above? Okay, so counterexample basically means that we're gonna have P implies Q is the original statement. Counterexample basically is you have P implies not Q. So this is an example of a counter example. Okay, counter example. If you have the original condition implying the opposite of the conclusion, then that's a counter example. Okay, so can we think of two lines that do not intersect on a plane? Is that possible? The option A says coplanar lines. Coplanar lines just simply means that two lines are on a plane, which is basically what the statement is saying, which is what this is. P is basically two lines on a plane. That's the hypothesis. It doesn't tell me anything. I want something that contradicts the conclusion, which is that they intersect. So the opposite of intersect basically means they do not intersect. If I can have two lines on a plane that do not intersect, then that do not intersect, then I have a conclusion. I have a counterexample. Okay. So this first option fails because two lines on a plane are coplanar lines are on a plane, which is basically my hypothesis. It doesn't contradict anything. It's not a counterexample. 2 parallel lines. If I have two parallel lines, can I find a plane that contains those two parallel lines? Exactly, you can, right? For every two parallel lines, there exists a plane that contains these two lines. I can put these two lines on a bigger plane, right? So if I have two parallel lines on a plane, do they ever intersect? Do these two lines ever intersect? Let's say this is line L and this is line M. If they're distinct lines, they never intersect, right? So parallel lines never intersect, so we basically have two lines on a plane which are parallel, but they never intersect. This is a perfect counterexample because you have P, two lines on a plane, and not Q, the opposite of the conclusion, they do not intersect. That's a counterexample. So our answer for this one is B. Okay? If you look at the other ones, perpendicular lines do intersect. Intersecting lines is just a intersecting lines is basically the conclusion of this statement. Okay, this conclusion of the original assumption. Okay, so the original assumption is false because we can find a counterexample. If you can find a counterexample to any statement, then that statement is false. Okay, all right. Let's move along to number 9. It says, which of the following serves as a counterexample to the conjecture below? Remember, counterexample basically is you have P implying not Q. Okay? So counterexample is you have the original statement implying the opposite of the conclusion. Okay? So it says if one pair of opposite sides of a quadrilateral is parallel, then the quadrilateral is a parallelogram. So we want to find a counterexample will be P, the original statement, the hypothesis, one pair of opposite sides is parallel, implying that the quadrilateral is not a parallelogram. This is a counterexample. If you can have the hypothesis implying the negation of the conclusion or the consequence, then you have a good counterexample. Okay? Now what we're going to do, ask ourselves which of these options is a quadrilateral with at least one set of opposite sides but is not a parallelogram. A parallelogram basically means that opposite sides are parallel. Opposite sides are parallel. Okay? If opposite sides are parallel, then you have a parallelogram. Okay? This is what it means to be a parallelogram. Now let's look at this cases right here. The rectangle. A rectangle, what is a rectangle? Or is a rectangle a parallelogram? Let's go over definitions real quick. Are opposite sides parallel? Absolutely. This side is parallel to this side, and that side is parallel to that side. This qualifies as a parallelogram. It has one pair of opposite sides but still a parallelogram. This is not a counterexample. A counterexample is a quadrilateral with one pair of opposite sides that is not a parallelogram. So scrap A. B. A rhombus. What is a rhombus? A rhombus is a parallelogram with 4 sides congruent. Okay? 4 congruent sides. So something like this is a rhombus. This side is parallel to that side. That side is parallel to that side. But guess what? All 4 sides are congruent. So 1, 2, 3, 4. All 4 sides are congruent. Alright? So is this a parallelogram? It is. It has one pair of congruent sides. So this is not a counterexample. Alright, let's take a look at C. A square. What is a square? A square is a special case of a parallelogram, of a rhombus, right? It's a special case of a rhombus because in a square, the diagonals are perpendicular, but in a rhombus, the diagonals are not perpendicular, do not always have to be perpendicular. So this one, opposite sides are congruent, are parallel, and all 4 sides are congruent, and the diagonals intersect at right angles. This one right here, the diagonals always, for a square, always intersect at 90 degrees. But for a rhombus, the diagonals do not have to intersect at 90 degrees. The diagonals are not right. Okay, that's the difference between a square and in a rhombus. Okay, and also the diagonals bisect at 90 degrees, and they are also, I'm sorry, the diagonals are congruent. That's what I meant to say. The diagonals of a square are congruent, but the diagonals of a rhombus are not congruent. So basically, this side is congruent to that side, that is congruent to that side. But if you look at a rhombus, the diagonals are not congruent. This is longer than this because it's switched somewhat. Okay, so I know that this is congruent to that. This is congruent to that. These two diagonals do not have to be congruent, but for a square it has to be. Alright, so this is a parallelogram. Even though it has one pair of parallel sides, it is a parallelogram, so this is not an example. Alright, so by method of elimination, the answer has to be D. Okay? How do I know? Because if I draw a trapezoid does in fact have, let me see, I have a trapezoid here. It doesn't have a trapezoid, so I have to draw one by hand. A trapezoid does in fact have one pair of parallel sides, but is it a parallelogram? Remember, for a parallelogram, all four sides has to be congruent, right? So we have a trapezoid like this. Does that have to be an isosceles trapezoid? In order for it to be trapezoid, it just has to have at least one pair of parallel sides. So this side is parallel to that side, one pair. But is this a parallelogram? No, because this side is not parallel to that side right there. They are not parallel. These two sides are non-parallel. Okay? So since it has one pair of parallel sides, it satisfies the hypothesis. But since it's not a parallelogram, this is P implying not Q, and this is a perfect counterexample for the original statement. Okay? So in order for it to be a parallelogram, instead of one pair, you must have two pairs. Okay? So there you have it. Alright, now let's move on to number 10. So for number 10, it says given TRAP is an isosceles trapezoid with diagonals RP and TA, which of the following must be true? So in this one, I'm going to draw a sketch of a parallelogram and then see what we can decipher from that. Okay? So I'm going to draw an isosceles trapezoid, the best of my ability. So let me sketch an isosceles trapezoid. Have to be accurate right here. And then we'll go over what the meaning of an isosceles trapezoid is. So let's see. I went 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 1 more. 7. Okay. Bam. Like that. And then we connect it to the one pair of parallel sides. So what does it mean for a trapezoid to be an isosceles trapezoid? Let's label it T-trap, T-R-A-P. So it's a trapezoid is isosceles when the non-parallel sides are congruent. So this side is congruent to this side. Okay. If this side is congruent to that side, you have a parallel line called by transversal. It also follows that the base angles are congruent, right? Base angles are congruent. This is congruent to that, and this is congruent to that. Okay. Same side interior angles are congruent anytime you have parallel lines called by transversal. Okay, so there you have it. Okay, so let's see. It says you also have diagonals RP and TA. So let's draw diagonal RP. This is diagonal RP right here, and diagonal TA. Alright, so which of the following must be true? RP is perpendicular to TA. RP is perpendicular to TA. RP is perpendicular to TA. If you look at the angles right here, does this look like a 90-degree angle? Absolutely not. It looks bigger than that, right? There's no condition that requires that these two lines intersect, okay? If it were a rhombus or a square, then it would be perpendicular, but in this case it's not. RP is parallel to TA. RP is parallel to TA. Absolutely not. They're not parallel lines. RP is congruent. RP is congruent to TA. RP is congruent to TA. Do we know that? Can we make that conclusion? If RP is congruent to TA, that means that we're saying that triangle TRA is congruent to triangle RAP. I mean PAR. Is triangle um triangle TRA, is it congruent to triangle PAR? Are they? Remember the rules for congruency, right? You can either have SSS, SAS, AAS, which is equal to SAA, or you can have ASA, right? Another version of SAS is HL, but we don't have to do that. Anyway, so are these two triangles congruent? If they are congruent, then that follows that TA is in fact congruent to RP. But guess what? We have S side congruent to this side, angle, because this angle is congruent to that side, because this side is congruent to this side by reflexive property, okay? So this one, based on the fact that it's isosceles, we have S. A, because parallel lines cut by a transversal, same side interior angles are congruent, we have A. And this side, RA is congruent to RA by reflexive property of congruency. So we have SAS. Bam. So these two triangles are congruent, so that follows that this side right here, TA, is in fact congruent to RP. Okay, so our final answer for this is C. Okay? Alright, just note that in these examples, we're doing a whole bunch of things in one question, so bear with me for that. They're just trying to make sure that you get a whole holistic understanding of the whole process, okay? Alright, so for question 11, we're asked a conditional statement. Which of the following is a counterexample? If a quadrilateral has perpendicular diagonals, then it is a rhombus. Counterexample, what on earth is that again? Let's review. Counterexample is basically P implies not Q. The hypothesis implying something other than the conclusion, basically, the opposite of the conclusion basically means that you have a counterexample and the original statement is false. Okay, so P in this case is the quadrilateral has perpendicular diagonals. Perpendicular diagonals, that's P. And the conclusion is it is a rhombus. So what I want is, I want perpendicular diagonals that is not a rhombus. If I can find a shape with perpendicular diagonals that is not a rhombus, that is not a rhombus, then I've arrived at a counterexample because I have P implying not Q. So let's look at these shapes right here. Which ones do you think has perpendicular diagonals? This does, this does. This is a square, right? If I assume this is a square, it absolutely does. This is a rectangle. Nope. Which of these is not a rhombus? This one looks like all four sides are congruent, right? In parallel. So this is totally a rhombus. This one looks like all four sides are all four sides are congruent, and opposite sides are parallel because this side is parallel to that side, and this side right here is parallel to this side also. So this is also rhombus, rhombus, rhombus. What I want is something that's not a rhombus because I want not Q. Check this out. Four sides are not parallel. This side is congruent to this side, and that side is congruent to that side because it's shorter. So this has perpendicular diagonals, but is not a rhombus. So this is my answer. The answer is A. Okay? Alright, so don't forget, a square is a special case of a rhombus. Okay? Not all rhombuses are squares, but all squares are rhombuses. Okay? And no rectangle is a rhombus, but all squares are rectangles based on the definition. Alright? So let's move on to the next example, number 12. Let's see, I have it here. No, okay, so number 12. It's back page. So number 12, we're going to look for a counterexample. It says the area of a parallelogram is a product of any base and any height. Which of the figures shows a counterexample to prove the following? So if I can have a base multiplied by the perpendicular height, that's fine. If it is based on the perpendicular height, that's the area. A is good. A checks out because you have base times the perpendicular height to that base. Okay? The second one, B. B is fine because you have the base times the perpendicular height from that base, right? So you also have a base times the perpendicular height. and the base, that 90 degrees means perpendicular height. So that's good also. C, we have the base times the perpendicular height. You see this base right here, since these two sides are congruent, like we have something like this. Since these two sides are congruent as a parallelogram, this is B and that is B, this is also the perpendicular height from the base. So that's good. As long as the base is perpendicular, as long as the height is a perpendicular base from the, as long as the height is perpendicular from the base, then it's fine. Okay, let's look at D. D, we have the base, but that is not the perpendicular height from the base. So this is wrong. This formula, this BH for here, is wrong. B times H, because the H is not perpendicular to the height. Okay, so the base times the height is not perpendicular to the base. So that is not the accurate height of this parallelogram. So this is wrong. This is a counterexample because you're having a case where one of the heights is not actually the height you need. So any height is wrong here. So this is your answer. The answer is D because you don't have the perpendicular height. All right, let's move on to question number 13. Question 13, it says, which triangles must be similar? So we're going to go over similarity real quick. What is required for two triangles to be similar? All right, so for number 13, it says which triangles must be similar. So the rules for similarity, basically, you have correspondence of the sides for the congruency postulates, and then just add one more additional component to it. So for similarity, you have all the congruency postulates, which are SSS, SAS, AAS, which is basically equivalent to SAA, and then you also have ASA. So if you have this S, is basically means congruent. I mean, they mean in proportion. They mean in proportion to each other. Okay, the sides are in proportion, and then the angles are congruent. Okay, that's what it means. And then we're just gonna add on one additional one, which is AAA or just AA, but this will suffice. So these 5 rules are the rules for similarity. Okay, these are the rules for similarity. All right. So which of these apply to these options right here in order to be similar? So for A, two obtuse triangles, that doesn't tell me anything about the angles. It doesn't tell me the angles are congruent or if any sides are in proportion. B, two scalene triangles with congruent bases. The bases are congruent. That's fine. That means we have S. That is not enough. We need to have, if we have S, we need to have SSS or AS or ASA. We just have congruent bases. That's not enough. That's not sufficient. So B is not an option. Let's look at C. Two right triangles. If we have two right triangles, let me sketch them for you. What on earth does that mean? If we have two right triangles, that basically means that we have two triangles with a 90-degree angle. Okay? What is that? If you have a 90 degree here, 90 degree here, two angles that are congruent is just A. That's not sufficient. If we have A, or just, if I just have AA, that will be sufficient. Okay? AAA or just AA, that's good enough. But I have only A. Only A is not enough for me to establish similarity. Okay? How about D? Two isosceles triangles with congruent vertex angles. That looks interesting. What does that look like? We have two isosceles triangles. I'm going to make them similar, somewhat similar. So let's say this is the first one, and this is the second one. You're told that they are isosceles. That means this side is congruent to that side, and this side is congruent to this side. Okay? You're told that the vertex angles are congruent. These are the vertex angles, okay, for an isosceles triangle. This angle is congruent to this angle, okay? So these two angles are congruent. What do we know about the base angles? We know that base angles of an isosceles triangle must be congruent, okay? So this angle right here is congruent to this angle right here, okay? So basically, let's say this were 30, for example. Then these two have to split 150 amongst themselves, right? So 180 minus 30 is 150. And then when you divide that by 2, you're going to have 75, right? So this is going to be 75, and this is also going to be 75. Since vertex angles are congruent, that means this also has to be 30 degrees. If this is 30 degrees, what does that follow? Since this is an isosceles triangle, the base angles must be congruent, right? So this is 30 degrees, and these are congruent. They must also be 75 and 75. So what do we have here? We have A for 30, 30, another A for 75, 75, and the other A. So we have A. This is sufficient to establish that two triangles are in fact similar. Alright, so the answer to this is D, because it satisfies one of my conditions for similarity up here, namely A. Okay? So it has to satisfy one of the conditions in order for it to be similar. Alright, let's move on to question 14. Question 14, it says, which of the following will be sufficient to prove that triangles ABC and DBE are similar? So question 14, where let's go over the rules for congruency again. All the rules, for similarity again. All the rules for congruency: SSS, corresponding sides and proportion; SAS, corresponding sides and proportion, and angles are congruent; AAS, what else? ASA. Remember, congruency is similarity on a one-to-one proportion. Okay, they're exactly the same, identical. Okay, but similarity is not restricted to 1-on-1. It could be 1 to 2. You know, 1/2 to 1. It can go in any direction you want. Okay, so congruence is just similarity at the one-to-one proportion ratio. Okay, so we got to add on one more attaché to this. So the AAA or AA sufficient. I like to say AAA, but they're both the same. Okay. All right. So which of these applies to this scenario right here? So let me see. Do I have a sketch? I think I have a sketch for this one. One number 14. There you go. All right. Which of them works here? So which of the following facts would be sufficient to prove that triangles are similar? So CE and BE are congruent. If this is congruent to that, that doesn't tell me anything. Okay? We're looking at the big triangle and the small triangle. These two are congruent. That just tells me that it just gives me S, because this won't be proportional to this in a ratio of 1 to 2. Okay, it's just S. So these two are in proportion at 1 to 2 ratio, and that doesn't tell me anything. All right, that's just S, which is insufficient. Angle ACE is a right triangle. This angle right here and this angle is a right triangle. No, I'm sorry. ACE is a right triangle. I'm sorry, I'm making assumptions here. If ACE is a right triangle, that is even less than an A. It doesn't tell me anything about this. What is this? Is this a right triangle? No, you don't know. ACE is a right triangle. That's not even A. So that's even worse. So it can be A, it can be B. AC and DE are parallel. If AC is parallel to DC, that means a lot. Okay? Because you have two parallel lines cut with transversals right there. What can that tell me? That tells me that this angle and this angle are corresponding angles. They must be congruent. This angle and this angle are corresponding angles. They must be congruent also. Okay? So what do we have here? This angle is congruent to itself by the reflexive property, right? So guess what? We have angle, A. We have another angle, A. We have another angle reflexive with itself, A. Perfect. This is one of the similarity rules or postulates, okay? So the answer is C. If you look at D, it says angle A is congruent to angle B. Angle A is congruent to angle B. That doesn't tell me much. Okay? That's inadequate. Alright, so basically that's the answer for 14. Now let's move on to question number 15. Question 15, it says, in the parallelogram below, ABCD below, which pairs of triangles can be established to be congruent to prove that triangle BAB is congruent to triangle BCD? So to prove triangles are congruent is either going to be SSS, SAS, AAS, which is the same thing as SAA, or ASA. Remember, ASS, and which is the same thing as SSA, these do not apply for congruency or even similarity either. Okay, so let's look at this. To prove that angle DAB is congruent to angle BCD, we notice that if we can show that these two triangles, you see, because this angle right here is part of this triangle, and this angle right here is part of this triangle. If we can show that these two triangles right here, this one and this one are congruent, then I think that should suffice. So angle ADC, nah, that's not what I want. Angle AED, no, that's not what I want. I want this big one right here and this big one right here, okay? DAB, and BCD. Voila, that's what I want. If these two angles are congruent, then I know that these two angles, if these two triangles are congruent, then I know that these two angles are congruent. So for number 15, your answer is C. Okay, there you have it. All right, let's move along to number 16. Number 16, it says, given two triangles, given if triangle ABC and XYZ are two triangles such that AB is proportional to AB over XY is equal to BC over YC, which of the following will be sufficient to prove that the triangles are similar? So for this one, if we can make a sketch of the triangles, then we can basically know what rule to use for this one. So for number 16, let's make a sketch of two triangles that are similar, okay? And then indicate the areas of proportionality and see if we can make it similar. So we have the first one like this, a bigger one, and let me clone this and make it a little bit smaller. Okay. All right. So let's say we have call this triangle ABC. Now we have to preserve the order in our arrangement here. ABC, and then this one is X, Y, Z. Okay. All right. So yes, you told that AB is proportional to XY. That's S, and BC is proportional to this side right here, and this side is proportional, that's S, and then this side right here, and this side right here, BC is proportional to YZ, that's another S. Now, in order for these two to be similar, we have the rules, right? It's either SSS, SAS, AAS, ASA, or AA, okay? In this case, we already have SS. All the options here involve angles. So in order for SAS to work, the angle must be between the two sides. It must be between the two sides. That's what SAS means. It means that the angle is included. So this angle right here must be congruent to this angle right here. Okay, so angle C must be congruent to angle Z, and the answer is C. Okay, because angle C has to be congruent to angle Z in order for it to meet the SAS congruency postulate. Okay? Alright, let's move on to number 17. Number 17 says in the parallelogram FGHI, IG and FH are drawn and intersect at point M. Which of the following statements must be true? So, we have a parallelogram with two diagonals that intersect at point M. Which of the following statements must be true? So, parallelogram could let's just draw an example of a parallelogram. See if I have an example here. Okay, there you have it. So there goes a parallelogram. This is one example of a parallelogram. Or we can even have, it could also be a square or a rectangle. Let's also look at a case of a square. Okay, these are parallelograms, two cases. Anyway, so you told that FGHI, so I'm going to call this FGHI, and this one is FGHI. Okay, so it says IG and FH intersect at point M. So you have the diagonals intersecting at point M. So this is the first one, and this is the second one, second diagonal. And this one is the first diagonal right here, and this is the second diagonal. They both intersect at point M. So this one intersects at point M. This intersects at point M. So it says which of the following must be true. So it says triangle FGI must be an obtuse triangle. FGI must be an obtuse triangle. In this case it is, right? But look here, is this an obtuse triangle? Absolutely not, because the biggest angle here is 90 degrees, so A is not an option. Okay? It can be A, because we have in the case of a rectangle, of a square, or a rectangle, well, this is a right triangle. That's the biggest this could possibly be. Alright, B. Triangle HIG must be an acute triangle. HIG must be an acute triangle. Is it acute? HIG? Let's see. HIG must be acute. Must that always be the case for this one? Look at this angle right here. This angle is not an acute angle. Okay, this angle is obtuse, so it's not always the case. If it were, this is a right angle here, so HIG does not always have to be an acute triangle. Because if I stretch out this parallelogram some more, you're going to see how big this can possibly be. This can be really, really big, way bigger than 90 degrees, so it's not acute. Alright, next one, it says triangle FMG must be congruent to HMG. So triangle FMG must be congruent to triangle HMG. FMG, HMG. Absolutely not. That's the case here because all these are congruent. But in this case, FMG and HMG are totally different. You can just look at it and tell. This is an acute triangle and this is an obtuse triangle. Absolutely not. They're not different. They're not the same. Okay? So the final answer has to be D, right? It says triangle GMH, triangle GMH is congruent to IMF. You can see it in both cases, right? Because this side right here is congruent to that side, right? And parallel lines congruent transversal. We know that this angle right here is congruent to that angle. Alternate interior angles. That angle right there is congruent to that angle. Alright, so you have ASA right there. This angle, this triangle right here is congruent to this triangle. Same thing here. That is congruent to that. This angle is congruent to this angle. Let's double that. And that angle is congruent to that angle. Remember, to establish congruency, ASA is one of the options. Okay? So there you have it. So the answer is there. Alright, let's move on to question 18. Question 18, you're asked, which of the following best describes the triangle shown below? So similar, incongruent, similar but not congruent, congruent but not similar, neither. Look at option C. Makes no sense because any triangle that's congruent must be similar. You see the similarity symbol? Means similar and equal combined. Congruent triangles are similar. Similarity is one-to-one congruency. Okay? So C makes no sense. Okay? So it could be similar and not congruent, but if it's congruent, it must be similar. Alright? So let's look at these two triangles. If this is 30, this is 90, this must be 60. Alright? Because we know it has to add up to 180. This is 60, this is 90. This must be 30 because the angles in a triangle, sum of angles in a triangle is 180. 888, guess what? These two triangles, this is angle, angle, we have A. Side, side, we have S. And we have A. So we have S, A. I'm sorry. We have A, S, A. We have A, S, and then A in that order. Okay? So by ASA, that means that they're congruent. But if it's congruent, it's also similar. So these two triangles are congruent by ASA and similar because all congruent triangles are similar. Alright, so our answer is B. They're both, oh wait, I'm sorry. The final answer is A. They're both similar and congruent. Okay? Alright, let's move on to question number 19. It says that which of the following statements must be true in order to show that GHI is congruent to triangle GHI is congruent to triangle JKL? Okay, so it says two angles must be scaling, two triangles must have exactly one acute angle. Alright, so let's take a look at this. So to prove a similarity in number 19, what we need is either for all three corresponding sides to be congruent, that will basically be SSS. So for number 19, we can either have SSS, all corresponding sides are congruent. We have ASA, SAS, AAS, which is like basically like AA plus another A. Okay. All right. So let's look at this. Two triangles must be scaling. That has nothing. Two triangles must have exactly one acute angle. That doesn't tell me anything. It doesn't even tell me if they're congruent or not. Or that one can just be A, and that's absolutely nothing. At least one of the sides of two triangles must be parallel. The one set of sides are parallel, that doesn't tell me if they're in proportion or congruent or anything like that. The corresponding sides of two triangles must be proportional. The corresponding sides of the two triangles. So if the corresponding sides are proportional, that is the definition of similarity. Similarity basically means that corresponding sides are proportional. This is what similarity basically means. Okay, so the answer to this is D. Alright, let's move along to question number 20. Which method listed below could not be used to prove two triangles are congruent? So for this one, basically, the rules for proving congruency are as follows. We're going to go over them again. To prove that two triangles are congruent, you have either SSS, SAS, ASA, and AAS. Okay, it's good to go over this over and over again so you don't forget, because these are critical. Alright, so prove that all three sets of corresponding sides are congruent. That is S. Voila, that's good. So we're looking for not, right? Which one is not good? So let's look over here. Let's see. Prove that all three sets of corresponding angles are congruent. That is A, A, A. What is AAA for? These four are for congruency. AAA is good for only similarity, but since the question asks for congruency, that means that this one does not apply. This one only applies for similarity, not congruency. These four are the only rules for congruency, okay? So keep that in mind. So basically that's what you have. The answer is B. Alright, so thanks for paying attention to this presentation. Do subscribe to my videos, and hopefully this helps get you ready for the CSTs.